Little boxes on the hillside, little boxes made of ticky-tack. Little boxes on the hillside, little boxes all the same. There's a green one and a pink one and a blue one and a yellow one. They're all made out of ticky-tacky. They all look just the same. And the people in the houses all went to the university, where they were put in boxes, and they came out all the same. And there's doctors and there's lawyers and business executives, and they're all made out of ticky-tacky. They all look just the same. And they all play on the golf course and drink their martinis dry. They all have pretty children. The children go to school, and the children go to summer camp, and then to the university, where they are put in boxes. They come out all the same. And the boys go into business and marry and raise a family in boxes made of ticky-tacky. They all look just the same. There's a green one and a pink one and a blue one and a yellow one. They're all made out of ticky-tacky. They all look just the same. All righty, everybody. How are we doing today? I need to remove this and that, and we will hold on. Give me just a second here. Maybe we'll do that. No. Man, I had this all set up. You know what I'm gonna do? I'll just go ahead and throw the. There we go. We'll throw this meter in front of that. Should move over there. Hope you all are having a great day. We're going to be playing with the Tesla coil today. Why is this so small? I'm not seeing the bottom of the meter. Man, I just had all this stuff set up. David had to go mess it all up by calling in. No, let me set this down for a second. Here's a cool shirt David made. A transformer from another dimension makes perfect sense. Good times for out of a conversation, a Skype conversation we had. Okay. What is going on here? It's not showing the bottom of the meter. It was just showing the bottom of the meter before. I guess we could do that. You guys really don't get to see it though. That's teeny tiny. What did I do? Why is this like this right here? It usually goes down to like here. Oh my goodness. I have it on this one? No. I'm pretty sure I had it like this. But the EMF meter I put right here, and it looked... Okay, I'm going to close out the EMF meter, and I will open it back up. Let's see. We're just going to go down for a second. There we go, folks. Okay, there we go. That's what I was looking for. All right, so I will turn you around and show you what we're going to be playing with here. That is it. So we have our Tesla coil, just a little guy, and I'll show you the power supply, I guess. No voodoo going on here. This is all coming out of the wall. It'll be plugged into this guy right here, a Daiwa DC power supply PS30XM. Goes up to 20 volts. My Tesla coil is only ranged for up to 12 volts, but we're not going to be pushing it today. Really, I don't even have to give it the 12 volts. I don't have to get up to 9 volts to show you what we're going to be showing today. But what you're seeing on screen, oh, sorry, we're not seeing it. I have to get EMF data right here. There we go. You know what I'm going to do? I'm going to use this phone to look at the chat so I don't have to get up and cross the room to read what you guys are saying and asking and all that kind of good stuff. Realign the deflector coil. Okay, so this is a GQ EMF 390. Really cool little device. Measures your EMF, electromagnetic field. It will do radio frequencies, but we have it set for EF, which is just your electric field. The styrofoam is just a insulator. We're going to kind of make our own new ground. Just because the Tesla coil isn't very big, so we're going to try to isolate the area that we're going to be showing you this stuff on. Now, what I found out is really cool. I have the power supply unplugged right now. Now watch what happens just by plugging in the power supply. It's not turned on or anything. But this meter will register it. It's wild how it does it. That time it really didn't do it. Huh. Okay. Well, we're plugged in. We don't have the power turned on yet. It's turned all the way down. We're going to flip on the power. Wow, look at that. Whoa, it just dampened the electric field around here to like nothing. So it made a new ground with this styrofoam box. Let's set it down over here. That's crazy. Put it back up here. Boom. And that's with, I mean, it's down to 0 volts, but that doesn't mean there's no power going into it. Isn't that wild? That was from me touching it, that big spike right there. So the electric field down here is 0. Now we're going to add a little. Wow, that's only at like 2 volts. Look at that. We'll turn it up about 9 volts. And here we're going to go to 12. Wow. And back down to 0. So what it's doing, actually, I'd like to show you guys this quick video. This is really, really, really interesting. Where did let's see. It's real quick. We're going to move this over here. Yeah, it won't take too long. Man, I had it pulled up. I don't know what I did, folks. So I'm going to go in here. I'm going to find the video real quick. Just give me a second. Bear with me. And this was shared by, I know how I can do it. That's how I found it last time. Okay. YouTube. Now we'll just go over here and do YouTube. Fractal woman. Oops. Her community. Okay. Now this is how a Tesla coil produces scalar waves. Let me just make sure. Can you guys, here, let me know if you can hear this. And I'm gonna have to mute this one. I know there's a way to do this a lot easier. There we go.
What is a purpose of a Tesla coil? Few people think Tesla coil is a fancy instrument, but only truth seekers know that a Tesla coil is a device invented by Tesla in order to create longitudinal electro. What is a purpose of a Tesla coil? Few people think Tesla coil is a fancy instrument, but only truth seekers know that a Tesla coil is a device invented by Tesla in order to create longitudinal electromagnetic waves. Okay, so for beginners, there are two types of waves in nature, in any system, which is transverse electromagnetic transverse waves and longitudinal waves. Transverse waves are the waves similar to wave created when you drop a stone in a pond of water. Longitudinal waves are the waves similar to the wave created by sounds in air. Everybody is familiar with these two concepts. But for some reason, we are taught that the electromagnetic waves are always transverse in nature, and they have the electric field and the magnetic field varying perpendicular to each other, also perpendicular to the direction of propagation. But believe it or not,
This is what Bob was saying about he was not taught this in nature. We're taught that all waves in nature are like this right here. And they're not. Our electric field does not do that. It's different. Okay, let's continue.
Tesla found that it is also possible to have longitudinal electromagnetic waves in nature. And for some reason, it's not called electromagnetic, it's called longitudinal magnetodielectric waves, or simply scalar waves, because.
So that's like electrostatic. That's a really complex way. Longitudinal magnetodielectric. Just say electrostatic. That's all they have to say. But you know how they like to make things super complicated.
In longitudinal component, you do not have a B field or a magnetic field. Everything is purely electrical, and one amazing thing is it looks like it's an electric field between two plates of a capacitor, which is what.
Now, where have we heard that before? Between two plates of a capacitor. Isn't that what Bob and I have been saying for a while now?
A magnetodielectric wave is. Now, let's see. If you want to, how these two waves are created. For example, take transverse electromagnetic waves. Transverse electromagnetic waves can be easily created by well-known system. You take a coil and you give an oscillating current to it. It produces transverse electromagnetic waves all along the surface, all along the lateral surface of the coil, and you can receive it using a simple dipole antenna, which is like this, and you can actually hear some sounds over here, and this is your receiver circuit. This is what a conventional well-known transverse wave transmitter receiver system is. Now, going to the second component, which is the longitudinal magnetodielectric or scalar waves,
or electrostatic.
how it is produced and how does it works. Okay, believe it or not, these waves are the waves created by a capacitor. Yes, it is created by a capacitor. Now, look at this diagram. What you have here is a battery connected to a capacitor. Once you close the switch, there will be a current going in, and there will be a displacement current going between these two plates. And according to C.P. Steinmetz, the famous and very famous and unnoticed electrical engineering and also a scientist, it's actually scalar waves being transmitted between one plate and the other plate of the capacitor. And this is what the longitudinal component is. Okay, the displacement current is a misunderstood concept. So if you assume that it is a scalar wave, let's see how a Tesla coil is producing this in huge amounts. Now, I am showing you a conventional diagram of well-known Tesla coil circuit. What you have over here is your main, and you have a high voltage transformer, in this case neon sign transformer. You step it up to several tens of kilovolts, and then you have what you have is a spark gap, you have a capacitor, and you have L1, L2. Everything is what you know already. But my question is, where is the longitudinal magnetodielectric wave created? Or in other words, where is the scalar wave created? Some people really think it's being created in the spark gap. Some people really think it's been created in the the coils. Some people, most people think it's been created by the L2 coil, which is this. And believe it or not, it's not the L2 coil, because what is created in the L2 coil is the conventional transverse wave, which is just created all along the lateral surface of the coil, L2 coil, and it is transverse in nature, and there is nothing different about it. In a Tesla coil in L2, you have a huge voltage being created if it is well tuned, about 30,000 to 1 million volts, which is quite large. Now, where is the scalar waves generated? Which part? The answer is, it is being created in the torus, or the metallic object which you place at the top of the L2 coil and the earth. Yes, if you don't understand what I'm saying, I'll show you this diagram. Yes.
Right there. Did you hear that? He said, and the earth. So let me back it up just a hair here. So this is the top of the Tesla coil. This is, the big globe on top of the giant Tesla towers. Mine is just a little flat washer. But this is where that electric field is coming out of. The top of and then the ground, the actual earth, is the other capacitor plate. So this is going to make this line right here. This line right here that goes through this torus is going to make this it's going to strengthen it from this part down. It's going to be stronger between this horizontal line right here. It doesn't stop right here, and the ground. It's so simple. I'm just flabbergasted that this isn't what we use really today.
Yes, what you see here is actually L2 coil, and you connect a metallic object at the top of the L2 coil, which I call it here as torus, and you have earth. So what you have here is a simple capacitor system, which is shown like here, where one plate of the capacitor is your torus, and the other plate of the capacitor is the entire earth, and the dielectric inside is the air present around the Tesla coil. And this is an asymmetrical capacitor. The reason is, one plate is the torus, which has a finite length, and the other plate is your entire earth, which is extremely large. So it's a asymmetrical capacitor, and it's basically a capacitor. Okay, so what you create here is
it's asymmetrical, though, as in the Gaussian surface here isn't equal to the earth. So it's not symmetrical per, but watch what it does. This is cool.
Electric field of high voltage and high frequency electric field. That's what you create between the torus and the earth, and that's what is your scalar waves. You see, these variations in the electric field, they propagate in space throughout the earth. That's how you transfer power and all those things. Okay, now coming back to wireless power and how it works. You have a transmitter Tesla coil at point A on Earth, and let's say you have receiver coils at point B and C of Earth. Well, when you create oscillating electric fields of high voltage and high frequency, it's received in B and C. The electricity is received at B and C, and this circuit is very unfamiliar to us. And I can
Do you hear that? It somehow does this, as in we don't know why it does this. I mean, how did Tesla figure this out? It's crazy, just crazy.
for for beginners, I can tell that it acts like as though this torus and this torus are connected through a wire. This torus and this torus are connected through a wire. Now, converting it into its electrical equivalent, this is the electrical equivalent of a Tesla wireless transmission system, according to me. So what you have here is a capacitor plate 1, and the other plate 2 is extremely large, okay, compared to the plate 1, and you apply a high voltage, high frequency oscillating voltage across these two plates, and you are using another plate over the left and the right side, and at this point and this point, and you're using the common plate which we use
Sorry,
for the transmitter for the receivers also.
Okay, so see, here's your Earth. This is the capacitor plate, the Earth. What he's saying is when you set a capacitor plate up here and put a charge to it, if you set up another capacitor plate here, it gets that charge. Now, I've heard that people can just take big giant plates of steel and put them up in the air and gather electricity off that. I've also heard of people laying down long pieces of wire underneath the electric cables and siphoning their electricity off that way. So yeah, wow.
And you're trying to take the output at these 2 points across these 2 plates, and somehow you're getting the output. And the system acts like as though this plate, the smaller plate over here, the center, and the smaller plates on the left and the right hand side are being connected by a wire, but they are not connected by a wire, but it looks like they are connected by a wire, and that's how Tesla was able to transmit power using earth as a conductor. And that's it. What is
I love that. And that's it. That's just how he ends it. I love it. Okay, we are going to share. How did I do this again now? Yeah. This one. And we will. No. Did it wrong. Oh, geez. Oh, Pete. Let me set this down for a second. We'll get to, well, okay, yeah, like this, but I want to have the voltmeter up here too. So we will bring up our voltmeter. I don't think you're going to be able to see that though when I do that. Okay. Now, why is it doing that now? Do I have to do this? Do I have to do this? Maybe that's the one. Okay. GQ EMF, there we go. Okay. So it's still, look at that. It is at 0. Now I will, man, that is wild. So it has made a new ground down in here. Now watch when I turn it, and it has no power really running to it. It's at the minimum. Whatever the minimum voltage is, that's what that Tesla coil is running at right now. I bet it's not even, nope, not even warm to the touch. Wow, I touched the transistor. Look at that. When I ground out the I better not be doing that kind of stuff. I don't know what I'm doing to the coil. Okay, so now we're gonna got a little spike there for me shutting off. Maybe, ooh, I'll ground all this out, zap all that energy that's in there out of there. So see, it'll read the electric field. We have those big spikes right there, so it'll take a second to show, but it's bouncing around because it's up off the ground and it's insulated. On the machine, it says it's bouncing between 14, 28, every once in a while bounce up into the 40s. Now we're back down to 7:30. Yeah, I'm just gonna wait. It's only gonna be a few more seconds. It looks like it's about 20 seconds away. But yeah, the machine now it's picking up the Earth's electric field. It's insulated, it's up off the ground, so it's not grounded out right now. So it's gathering current from the air right now. There's voltage in the air. We'll see it right here. See that? It's bouncing around a little bit. Now we're leveling out a little bit more. Things are calming down. Now remember, electricity, it's kind of like temperature. It doesn't all just dissipate immediately all the time. If there's nothing for it to get to ground, it's going to have to discharge all that extra potential just out into the air, and it doesn't happen like that. It takes a second. So now we got our baseline. Now watch this. It's still not at zero. I'm seeing it bounce around 5, 6, something like that. We got to wait for this other little spike to get out of here. And you'll see it's bouncing around real well. We got a nice, we're getting about 3 volts per meter between 0 and 3 volts. So it's real close to the ground, but it's not touching the ground. It's not neutral. Now I'm going to turn it on, the Tesla coil, and we're going to leave the power turned down all the way. So this is just the minimum. It's going to be getting a little tiny charge, but boom. Look at that electric field just stop. Oh, dang it. I'm sorry, guys. You guys aren't really seeing what I'm seeing here. No, what am I doing? There we go, maybe. Give it a sec. Is it gonna pop up? No. Okay, hold on, we're gonna stop the screen share. Screen share, share screen, this one, share. We're gonna go like that, and that. And hopefully that's gonna make this EMF meter a lot bigger so you guys can see what's going on here. No, it's still not. I want my EMF meter. You guys aren't seeing my EMF meter. That's the thing here. Oh, just stepped on the cord. Oh, whippersnappers. I mean, can you guys see it? Um, I mean, I can put it over here. And no. No, what did I just do? Oh, I know that the only thing that stinks is when I make it full screen like this. There, you guys should be able to see it a little bit better. I don't know if it's let me see. It would help if I turned it off of 144. Oh yeah, I guess you guys can see that then. That's the best I can do it. I can't make this any bigger. Okay. All right, so we have all that nonsense out of the way there. Yeah, that maybe Jaren could teach them how to write a better program because they need to work on this EMF meter. I can't even download data off of this and then load it into this and play it back and watch this. It'll only come out in a spreadsheet, which I know you can do that, but that's, I don't know. Okay. So you can see, look at that baseline there. EMF max, 0 volts per meter. I will turn off the power again. We will touch this and this. It's going to give a big giant spike because I discharged it. Now it'd take forever, but I'm still seeing 0 here. Oh, there we go. I had to touch the styrofoam in here as well. Wow. Okay. Now here's the really interesting part, folks. We're going to take the EMF meter and we're going to set it up here above our Tesla coil. Now, if you remember from that video, the Tesla coil goes out this way and down. So what is that going to do to the area right above the Tesla coil up here? What is that going to do to all this up here? Let me discharge this a little bit. It's amazing how much styrofoam will hold an electric charge for how long. You know, that's what a resistor does. When you have your, or not a resistor, excuse me, a insulator. It's not letting go of the electricity. A conductor, it goes right through it, onto the next spot, but a resistor holds it. And it's neat, once you run this Tesla coil by a piece of styrofoam for a long time, it really holds that charge in here. It's crazy how it does it. Okay, so let's see, our meter is bouncing around. It is a little bit up off the ground. As you can see, our minimum, we'll see where it kind of levels out at now. Looks like it's about 56 volts maximum, that top part up there. But as you can see, it's not dropping below now. It's not going back down to the 1.9 volts. It'll give us our minimum here in a second. You know, they need to make it so you can turn that down to like 10 seconds instead of having to wait a full minute to see all that stuff. Like the highs and lows. I'm sure there is a way. Okay, we're just waiting and waiting and waiting, and our minimum is 41 volts. So we're about maybe 18 inches up off the ground here, our meter. And we're basing out at 44 volts to 56 volts, right in this area of the air right here. That's what we're picking up. Now our power source is turned off. We're going to go ahead and turn it on right now. I saw a little dip there, but okay. Now this would be neat. Remember, that's like the minimum. It's barely getting any power. Now I'm going to turn it up to about 2 volts. And we're going to watch what that baseline does. Whoa, it's not doing it. Maybe I have to be closer? Turn it back down to 0. Well, there it zeroed out. Okay, let me turn the machine off. Hit all of this styrofoam here, discharge the Tesla coil. Okay. Now it's just a waiting game, waiting about 25 seconds for that. Yeah, there's got to be a way to, let me see if I can't move these lines around here. No, I can put a line in there, but it doesn't really stop the 60 seconds and all that stuff. Okay. So, I mean, we'll get an average reading. We'll be able to see the reading. So it's been running for about, what, maybe 30 seconds with the Tesla coil turned off, discharged. And that's kind of our baseline right there. Now I'm going to turn it on with no power. Little bitty jump there, and then we're going to turn it up a little bit. What is going on? So I had to turn it up and then back down. But look what it does now. It's so this is getting the minimum. I had to turn it up a little bit, and then I turned it back down. But I am getting it as if it's on the ground now. Let me discharge this. No, it's still, because there's power running to it, it's at the minimum, but it's like it's made a new electric field. If we set it down here right now, what's it going to do? Now that kind of wow, this is really weird. Yeah, I showed this to Bob the other day and it wasn't doing this. I don't know what I have set up different. Maybe I'm too far away from it. Let's turn that down, turn that off. Discharge, discharge. Yeah, what happened the last few times I was doing this? Let me just separate these capacitors a little bit here. Okay. Discharge, discharge. Okay. It shouldn't be reading 0. Oh, I bet our styrofoam is holding a lot of this charge into it. Come on, get out of there. Okay, we're getting it to bounce around a little bit again. Doing its thing. Now we'll try to do this again. This is weird. There we go. With the Tesla coil running at minimum, it's like it's created a new field up here, a new baseline. There's my hand getting a little too close. Yeah, and this right here, watch, I can just put my finger close to it. This will show you that I'm grounded right now with the ground, barefoot, nothing on, and this thing is up in the air. So the potential from my finger to the ground should be different than the meter. When I get just close to it, you'll get that little spike. Are we? A lot of discharging coming off of this styrofoam. I need to get more pieces of styrofoam. I save it all. Okay. If I run into myself. Okay, so we have our baseline. Power is off to the Tesla coil. Maybe because these two are both sitting down on the, I'm gonna prop these up. There we go. And this one. There we go. Okay. It's tricky playing with electricity and trying to keep it where you want it to be to get to a certain thing. I mean, there's so much going on that we can't see with the electric field. I would love to have a pair of glasses. Okay, so we got our baseline, 4.5 volts, all the way up to 52. It's really jumping around right now a lot. That's interesting. I believe we are coming up to the time of the day where it pulses. It starts around 4. No, we're past that. We might, let's see, 7 UTC is the maximum, I think. Or is that when it starts? No, it starts at 7 UTC. Max is out at like 1 or 2, and then by, I think 1, and then by 4, it's back down. Yeah, I haven't seen these readings yet like this. That's a big jump between 11.5 volts and 51 volts. Okay, back to the test coil. We're going to do it one more time. We'll play around, and then I'm probably just going to wrap this one up, folks. Let's see here. So our voltage is turned all the way down. We just turned it on. No voltage going to it. It really didn't affect it as much this time. There goes Hank Pank. Okay, we're going to add about 2 volts. Wow. I'm even more lost than I was 2 weeks ago. But it's really jumping around now. It's saying it's above 400 volts. the whole time on the meter, but that doesn't mean anything. I've noticed that the meter and the meter is not timed as much as the graph. The data is still there in the machine. It's more of a roundabout on the actual screen of the meter. Whereas you plug it in, you get like real accurate down to the second data. So let's see what our new baseline is. 193 to 247. That's with 2 volts of electricity. We've increased the electricity in the air around here that much. Now we're going to go up. It's about 9 volts right there. Okay. Turn it back down. I think I might have freaked out the meter. Still reading. Thank God. Turn that off, discharge that. Discharge all this styrofoam here. Just set it on the ground. Man, that was only at like 9 volts. Go to that. Okay, we will set the test coil up. Yeah, I swear, every time I do this, I think, so much of it is trial and error. I can't tell you how many hundreds of hours I have sat around playing with, just like balloons, and they call them electrostatic rods. It's just like a rod of glass with silk, or what was the other one? A piece of rubber with cat fur, and just rubbing those and putting it onto a balloon and measuring how long the polarity would last. I mean, you could polarize a balloon to where if you took, something positive like the Van de Graaff generator, and I would put it near the balloon would spin until that opposite pole was facing it. It's amazing how certain things hold electricity, and I mean they hold it. I mean, for a long time. I had polarized a balloon. I had them hanging from my ceiling for weeks. But yeah, just hundreds and hundreds of hours of playing around with this stuff to really get it. And I think that's how a lot of the guys that actually do stuff, you know, do it. They just try things. You just play. It's that simple. It's it's fun. I can't say it any better way than that. It's the stuff that our children should be doing in schools. You know, just playing with this kind of stuff. And I never saw a Tesla coil in school. I never saw any of this stuff in school. Taught how any of it worked. Yeah, it's an amazing world out there. It really is. And there's a lot of people out there looking and sharing. So thank you all that are, you know, helping out with all that kind of stuff. I'm gonna get out of here. I don't even know how long the stream is, yada yada. But it was fun. I had fun sharing. I learned some stuff. I'm gonna sit here and play with it for probably most of the afternoon, trying to figure out what changed in here, what is different. I mean, electricity is usually pretty. It is or it isn't, you know. But there are those weird. I mean, when you're dealing with the electric field, it's a heart beating and it's alive. So just because it's always usually doing something doesn't mean it's always going to be doing something. Our EKGs go out of whack every once in a while. You know, this place is alive. It's got a heartbeat. It just showed that. But you can, yeah. And the Tesla coil, I think, was only like that one was like $40. So, I mean, they're not too bad to play with. They run on 9-volt batteries. Power supplies are a lot better. You go through a lot less batteries that way. But they get expensive. So, I mean, yeah, that could be it too, Bob. The humidity is way different. That's one thing that crazy affects electrostatics is the humidity and the temperature and all that kind of stuff. So I'm hoping for a nice, cool, dry Flattoberfest weekend. That's what I'm hoping for. So I can show some of this stuff, you know, working how it's supposed to. But yeah, that's it, folks. I'm gonna get out of here. Thank you all for joining me. That was fun. We'll do it again. We'll as soon as I figure out what's going on, or even if not, maybe we'll just start doing this after Karen B every week. This is fun. We can play with all the different toys. You guys can pick Faraday cages, Tesla coils, the generators. There's all kinds of stuff we can do, all kinds of stuff we can play with. So, love y'all. You guys have a great rest of your day, evening, night, whatever it is. Much love. And yeah, thanks for joining me. We'll see you later. Bye.